Hello, everyone, and welcome. My name is Jonas Mortensen, and I'm here to give a talk on the new URP Sample Scene. So over the next 30 minutes, I'll go through some of the design considerations we had when we built the project, as well as talk a bit about the more technical stuff, how we solved some of the problems, and in the end, talk a bit about performance. We wanted this to run on as many platforms as possible. That meant we had to cut some corners and make some conscious decisions when setting up our pipeline assets. But first, I hope to show you a video. Thank you. Yeah, so as most of you probably know, when you start a new project in Unity, you start in the hub and create a new project, and you get to select from a list of templates. And until this point, the only template with any content for URP has been this thing you're seeing on the left here, the construction site. And this scene is pretty old by now. It was made back when URP was really young. And that means that a lot of the features that we want to show off, a lot of the latest and greatest features of URP, they're not really being shown in this scene. So we needed something new for that. It's also not great to start new projects in this scene, because with the stuff that's there, you kind of have to do a bit of cleanup before you can actually start game development. But that's where the blank templates come in. So they came to the SIPs a bit later. And as I said, really great to start new projects, because they're just ready to go, empty. And then also HTRP has its sample scene, and that's really what we're trying to do with the URP sample scene as well. It was very much focused on learning, and it really explained to users how the workflows in URP work, and also had in-editor tutorials and all this kind of stuff to kind of onboard you with the pipeline, and that's exactly what we wanted for this sample. So we had a few requirements when designing it. We wanted something that could show URP scaling to a wide range of platforms. We wanted something that could show URP in a photorealistic context as well. We wanted something that could show how to customize URP and enable unique aesthetics for your games. And then we also wanted to enable users to do look dev on their assets and have an area where you can drop in your stuff and just see how it looks in URP. And we quickly realized that this wasn't going to be possible with a single scene, so we decided to build separate scenes for each of these requirements. We built the garden, which uses URP PBR shaders to build an environment targeting mobile and consoles like Nintendo Switch, as well as PC and high-end. We're also building the Oasis, which uses VFX graph and high detail assets and speed tree to convey photorealism on devices that support compute shaders. Then we're building the cockpit, which uses custom lighting in shader graph to do stylized, efficient rendering, targeting standalone VR headset like the MetaQuest 2. And then we have the terminal that kind of ties everything together in a museum-like fashion where you can move between the different areas in a seamless transition. And talking about moving between the scenes, having several scenes gave us this opportunity to do something cool when you traverse between them. And we wanted something that was seamless and came up with this idea of having these screens in rooms, and when you enter the room, they kind of turn on. And if you interact with this control panel that's in the middle, you'll then dissolve everything around you and eventually end up at this new location. So I want to talk a bit about how we made this in URP. It's a couple of components. There's an off-screen render target that then renders whatever on the screen off the actual screen. So on the monitors in the room, that stuff is rendered off-screen. And then there's a custom shader that samples that texture, and that shader runs on the actual screen surfaces themselves. Then there's a stencil mask that we use to stencil the full screen effect of the dissolve effect. Then the actual full screen effect of dissolving everything. So those are kind of the components, and I'll go a bit more into detail. The scenes are loaded as we need them, or enabled rather. They're actually all loaded in the beginning of the game, and then we enable and disable them based on what we need. And you can see that here that there are the two cameras. There's one in the actual terminal rendering the room, and then there's another camera offset that rendering off-screen. And then we enable and disable as we need them. And they are following each other completely one-to-one. And then when you transition to this new location, we just swap the positions of these two cameras at a point where it will be a seamless swap. In URP, we allow for a single shadow casting directional light. This is also called the main light. And between the different scenes, this light will be different. So one scene is a night scene, so it'll have a different angle, might even have a different tint, it might even be baked. So we need to be able to set this per scene that these lights will be different, because we only have one at maximum in URP. So we do this on the onBegin camera rendering callback. And here we can then check on it based on the tag and kind of disable the lights as we need them. So within a single frame, I say a single frame, but that's actually two cameras rendering. When the one camera is rendering, there's one light that's the main light, and when the other camera is rendering, it's another light. And the same goes for environment settings in general. So URP, or Unity rather, has this concept of render settings. That's your skybox, and that's your general ambient lighting. And that needs to be different as well, because of course in a night scene, you need a different skybox than a day scene. So we handle that in here as well. Just checking to see which camera is currently rendering, and then we have some constructs for getting the actual skybox and reflections and stuff like that, and then set them based on camera. And that enables us to do something like this, where you're having it's an actual split screen setup of two cameras rendering the same thing, but then they have drastically different lighting setups, even though they're loaded at the same time. To make the transition seamless, we needed the screens to fade from having PBR properties like reflection to being the completely raw render texture, so it would be seamless when we swap them eventually. We did this in shader graph, and doing the actual just raw render texture is easy. It's just sampling the texture that was rendered by the previous camera, and then just using an unlit shader graph. But then adding the reflections in were a bit more of a challenge. And we do this using custom function nodes in shader graph. And these are really powerful, especially if you want to hook into some of this shader API that are in the SRPs. You can use them to write any kind of HLSL, which is super powerful. But as I said, if you know the shader library, you can take advantage of that. So in a separate file, we defined this URP reflection function. And then here we call glossy environment reflection, which is a shader library function from URP. And this means that we get all the support that we need. So there is actually a reflection probe node in shader graph already, but it has some limits as it only supports a single reflection probe, so you won't get blending between them. We also rely on box projection in the room to get accurate reflections, or at least more accurate reflections. But that's not supported by the reflection node in shader graph. So what we do instead is call this function that then has all the stuff needed from us. So we could basically get the same support for reflections in our shader, our custom shader, that the URP lit shader has as well. There is a quirk in shader graph where all the shader graph previews, the one you actually see in the shader graph editor, are all rendered using built-in, so the legacy pipeline. So it's really handy whenever you're doing pipeline-specific HLSL in custom function nodes, is to wrap them in these shader graph previews. That means that you won't get any undefined deep behavior when you're editing your graph. You can come into a situation where it won't compile in the editor because it's running built-in, but it will compile in the actual game view. But this will then make sure that it compiles everywhere. And you can do whatever you want inside the preview. And in this case, I was just lazy and made it black. Then after we've set up the node, or written the node rather, we can then start hooking up stuff. And I guess this is another shader graph tip that it can take a lot of setup to connect all these things. So the glossy reflection function, it requires some data, like world space position and such. And you have to hook these up every single time. And this can be kind of tedious. You have to do this every time. So what's really beneficial is to wrap it in a subgraph. So you, instead of having to do this setup every time, you do it once inside the subgraph. And you can also choose what to expose and what to not expose. So in this case, inside the subgraph, I have the actual custom function node where I sample world position, view direction, everything. But then one step up, it just looks like any other node. And I can then create it from anywhere. And I've basically started creating my own like shader, like URP graphics node library by doing this. And yeah, the result is this chrome-like material that has completely reflections, no lighting, except for working with the URP reflections. And then actual surfaces like this, they become a bit less reflective as you view them at an angle. So we just capture this by multiplying with a Fresnel mask and get something that looks like a screen and that we have completely control over. So we can fade these out completely as we need it. Yeah, so the reflection is added on top of the color, and the color is then either black if the screen is on, or it's the actual off-screen render texture if it's on. And talking about on and off, we have this subgraph that's about transitioning. It's kind of a crossfade between the black color and then the render texture, in this case, just this weird salmon-y color. And this is driven by a grayscale value. So in this example, I'm using a Voronoi noise. And just stepping it, and then based on a distance, I can get this edge effect that I color with an HDR color. But we could basically use anything instead for the grayscale value. So we can make this driven by a texture instead. And I just here have a couple of examples of what it would look like using a texture. And the idea we had for the dissolve effect, that meant we went for the bottom right one, this kind of pixelated gradient. And yeah. So and it's really cool, or it's very easy to iterate on effects when you have something texture driven like this. You can just create a new texture and plug it in and see what it looks like. So very cool for experimenting. Next up is doing the dissolve effect. So this is a full screen effect, and we used URP's full screen renderer pass renderer feature, which is a really easy way to do custom post-processing. It's just on the renderer, you add this thing, and then in ShaderGraph, you can completely build your custom image effects. We use the same crossfade functionality from before, so the one you saw here. We put this into a subgraph, and then we can use that again here. Instead of using a texture, though, we're using this other subgraph that just generates like a pixelated noise grid in world space. And we can just use this to do the actual crossfading. But the problem is that now it becomes completely black, and what we wanted was to just leave the screens untouched. So we can do this in URP as well with the built-in render objects renderer feature. So adding this, we can do another pass that renders the screens one more time, but this time they write to stencil. And then they will write a stencil value of 1, and then in the actual shader graph, which you can see on the bottom left, we then check against this stencil and check, okay, don't render the post-processing effects in all the fragments that have the 1. And like that, we can then create the transition itself. So the result is this: you turn the screens on, you start dissolving the world except for the screens, and then at the point where the raw render texture is displayed and everything is black, you can then swap the positions and fade it back in. Moving on, I want to talk a bit about lighting in URP. Standalone VR is increasing in popularity, and it has some quite hard requirements on how to get it running. So it's, of course, a lot of pixels. You're practically rendering the game twice, once for each eye. And they also have big FPS requirements. On the MetaQuest 2, you're basically looking at running it at 72 FPS minimum. So that means that the URP PBR-led shader is often too expensive to run on something like the Quest. We have additional shaders in URP. We have the simple lit and the baked lit, and these are much cheaper. They run at cheaper BRDF, and they also skip reflections and specular contribution. You can see, like if the content is right, the difference is very hard to notice, but of course, the floating metal sphere doesn't get any reflections when using simple lit. And that's maybe the case where you would do one shader for the majority of the environment, but then sacrifice the cost of the lit shader for the surfaces that really need it. A different approach is to do custom lighting inside of shader graph. And that's what I'm doing here on the right. And when you are in full control, you can basically cut corners and make it more efficient. So in this case, it works really well. There's probably a lot of other cases where the example on the right would not look accurate at all. But that's the power you have with doing custom lighting. And another benefit of doing custom lighting is that you can get creative with it, right? So you can start doing your own crazy lighting functions that have no reason that they're not physically accurate at all, but it works for your game. And we wanted to show this workflow in the sample scene as well. So similar to before, where we did the glossy reflections in using the URP shader library, we're now getting data from the pipeline that we can then use in our shaders. And in this case, we're getting the main light. And there's a pretty easy, simple function for this, which is called get main light. And then to get shadows as well, we provide some shadow coordinates. And these are also obtained just from well position with another helper function from the URP shader library. And again, we wrap it in a shader graph preview and put in some values so we get meaningful previews in shader graph. And now with a simple dot product, we can get custom lighting in our shaders. That's really efficient. And we can then build on top of this and add the features we need and basically get as fast as we can. In the cockpit scene, this is what we did, but we wanted something that was a bit more toony. So we're doing a smooth step on this dot product. We could do a regular step as well, as doing a smooth step is a bit more expensive, but the thing with steps, and they're like completely binary, so if you don't have any fragment anti-aliasing, they will alias quite bad. So especially if you have very large pixels, and like in the case of the switch, having aliasing is something you want to avoid. The recommendation on Quest is to run MSAA, and MSAA doesn't treat fragment aliasing, so you really want to keep that to a minimum, and that's where the smooth step really comes handy. For ambient lighting, we baked a light map outside of Unity and then edited it in Photoshop to get it a bit more stylized, and then pulled it back in and added it to the shader. And this is another example of why doing custom lighting is a really powerful thing. You can pick and choose what you need from the editor. So in this case, we wanted to not use the Unity's light mapper because it's very physically based, and then instead do our own thing. And we were able to do that with the custom lighting. The last thing we did to make the lighting stand out a little bit more was to add a fake diffraction effect. I hope you can see it, but it's this thing around the edges where the light goes a bit red. So what we're doing is we're sampling the shadow map multiple times, and then based on the difference between them, we can then isolate this area around the shadows and tint it a bit red to kind of just introduce some warmth and simulate that light have kind of bent as it entered the cockpit. And this is all inside the project, by the way. So once it's released, you'll be able to look at all these graphs, and they'll be documented well, so you can understand what's going on. The last thing we did was add an outline effect. This was also done entirely without code, using the same renderer feature as before, the full screen pass that injects it. And it works quite simple. It's just sampling the world space normals at different offset positions, and then does a bunch of dot products and multiplications to kind of do edge detection on this normal map. It's a bit subtle, but it really helps everything come together and unifies the art style. Now, writing custom function nodes that hook into the URP lighting requires a lot of knowledge on the pipeline. And it also requires a lot of knowledge on the shader library. And getting familiar with these things is no easy task. The documentation at the moment is quite lacking. There's also no concept of public APIs in HLSL. So if URP team changes some of the APIs, there probably won't be an automatic upgrade for you to rely on. But Unity is working hard to replace this workflow. It's called block shaders, and it kind of tries to do this in a simple and cross-pipeline and well-documented way. You can already try block shaders out now if you're interested in doing some custom stuff. There's a link there, but that doesn't mean a lot to you. But if you go to the Unity forums, there's a shaders section there where you can download the prototype, and I recommend that. We need the feedback as well, so please do. A couple of notes on the garden, which is the scene we have with the largest amount of unique assets, which will, of course, all be available when it releases. And they're all built modularly, so you can extend the area, or you can build an entirely new area with all this. Having this amount of geometry meant that we had some challenges when doing the actual rendering. We wanted it to be at night, so we wanted a lot of real-time lights. That meant that we couldn't do additional light shadows for all these tiny lights, only for a couple of major ones. So what we did instead was bake cookies for all these, all the lights, and it works very well. You get some light leaking when you're doing cookies instead of shadows, but those can be alleviated with rendering layers. So you basically, if you have a lamp that's close to a wall, then you might get some light on the floor in the room that's next in the next room. But then you can put the floor in that room and the light on different layers so they won't affect each other, and kind of get around it that way. And that's another benefit of having modular assets, is that you can very easily separate your level like this. And then for the vegetation shader, we, as I said, had a lot of lights, so we wanted this to also have some translucency and react well to lighting. So similar to the get main light, we did a light loop in a custom function node in the shader graph. And then we can use that value and multiply it with a subsurface scattering map, and then pipe that into the emission to give this the light kind of a glow around the light as it moves through the plants. Moving on, I want to talk a bit about performance. With quality settings and pipeline assets and renderers and renderer features, there are a lot of stuff to configure in URP. And it can be kind of a challenge. So the first thing I would say is you should profile your apps every time you are trying to configure for some target. And the profiler is great. It really helps you get an idea of of the CPU usage in your app. But another cool thing is the frame debugger, which you see on the right. And a lot of the settings that you're making in URP, or the decisions you're making, they have a concrete impact on the list of passes that are in your frame. And the frame debugger is just really useful. I keep it open all the time whenever I configure for some target. I always have it open, and I can see, okay, when I enable this thing, it injects these passes. Okay, I'm trying to avoid this thing. Is it happening? It is. Figure out why and update. It's the only way to be sure that you're getting the frame that you're actually expecting. When configuring graphic settings, it's important to know the architecture of the hardware you're targeting. And the main thing to be aware of is whether the GPU is tile-based or not. So if you're developing for mobile hardware, it's more than likely the case that it's tile-based. And if that's the case, there are a couple of things to know and avoid. The first one is limited bandwidth. So you should avoid features that have dependencies on very large full-screen textures, so you avoid sampling them. Then they also have a lot of pixels often, these devices. So in URP, it's a matter of reducing a slider to change the render scale. And that can give you a lot of frames back without being noticeable in the app at all. We also have FSR if you want to upscale it, but even that is usually not needed. Pixels are so small on modern mobile phones, so you can usually get away with it. These devices also do pass merge optimization. So that means that if you have several passes in your frame that are rendering to the same render target, these can be merged together for performance benefit. So you want to stay away from injecting stuff inside of these passes and kind of leave the optimizer to do its thing. There are a couple of ways to make sure you do that in URP. I'll talk a bit more about them. Yeah, let's move on. In URP, we have 3 rendering paths, and they all have benefits and drawbacks. The first one is forward, which is the oldest one. It has a per object light limit. So that means that at any given time, a specific object can only have so many lights. And you can see on the left here that doesn't work very well for the garden scene. We have the gravel that's not receiving a lot of light from these lanterns. So it doesn't really work. It can be really cheap, though. You can also have vertex lighting that really reduces the cost of your application. Then we have deferred, which is much better at scaling lights. It's a bit harder, or it's a lot harder to do custom lighting in deferred, though. So if you look at the plants that are in the lower left of the center image here, you can see that they don't get that glowing light effect. So stuff like that is harder in deferred. It's a bit more rigid as a rendering path. And then we have Forward Plus, which is kind of the best of both worlds, but it's at a cost. So it structures the light different, so you don't have this per object light limit anymore, but it needs to spend some time to actually build this data structure. It's very optimized for mobile though, so especially on high end where you have the GPU capabilities, I would suggest to go with Forward Plus for those devices. I want to touch a bit about depth priming. In scenes with a lot of overdraw, which means that some pixels are getting drawn to several times during the frame, you can use depth priming to alleviate that. It works by injecting a pre-pass, so before anything else, that renders the depth of the scene, and then you can use this depth buffer to kind of compare as you're rendering with the more expensive fragments. This is usually a very great optimization, especially on PC. The thing about mobile is that the mobile hardware usually does this on the chip. So you already get hidden surface removal on the mobile chip, which means that the benefit of doing the depth priming is you're not really getting it. You're just paying for the pre-pass, but all the fragments are going to be on screen anyway. They're not going to be overdrawn. So you're just paying extra costs. And even though you're not doing depth priming, you might still be getting a pre-pass. And that's because in URP, there are a couple of features that inject pre-passes. And they are decals and screen space ambient occlusion. Decals are very easy to configure to behave accordingly. There is an automatic mode there. And automatic just means that on mobile, it'll run the screen space mode, and that doesn't require any pre-pass. But you can still force it if you really need to use the debuffer, you can use it. The difference between the two is the surface properties that it can affect. So debuffer decals can affect stuff like metallic and smoothness and AO, where the screen space ones are only the albedo. But you should be careful about using debuffer on mobile because it basically requires a lot of full screen textures, which is a lot of memory and a lot of bandwidth. So keep it in automatic. SSAO is a bit more difficult to configure. You have to enable after opaques, which means that instead of doing the SSAO in the opaque pass, relying on a pre-pass, it'll do it afterwards, using the depth from the opaque pass itself. You also need to disable normals from the source, because normals can only come from a pre-pass. So instead, we recreate them from depth if you disable the normals. So in SSAO, enable after opaques and remove normals from the source. That removes the dependency on the pre-pass, and you're getting performant SSAO. Sometimes, though, I'm sorry if it seems convoluted, but sometimes you need a pre-pass. This is especially true for the Quest 2. That's often a very fragment-bound device. So you have a lot of pixels. You need to do there's a lot of pixels on screen and not a lot of GPU to kind of power it. And in that case, the depth copy can be quite expensive. So that's where we have the depth texture mode. That's called force pre-pass. So you can do a pre-pass without doing the priming, and that'll save you a depth copy, which can mean a lot of performance. It can basically make or break your performance on Quest. We did, okay, I'm a bit behind here, so I think I'll just skip this. I'll talk about it quickly. So we had to scale our post-processing, because that's not something that's supported out of the box with Unity. So what we did was we wrote this renderer feature that just manages an object. It's basically at runtime, it creates a game object, and then based on the quality settings that are currently enabled, it'll then set a volume profile and set the volume profile with the settings that we need. And doing this was kind of important to get us running with the FPS we needed on the iPad. I'll skip the recap. Okay, so I know that was a lot, but I hope that by now you're interested in the project and would like to poke at it yourself. And being a template, this will be released in the Unity Hub. It will replace the existing construction site scene, and there are a lot of moving parts and possibilities for bugs. So we are doing a soft release first in the 23.2 beta version of the editor. And then when we're confident that it's stable, we'll do the LTS versions as well. And we have it in the expo floor as well. So please come by and have a chat and take a look at the project. We have it running on an iPhone and an iPad and on PC as well. And a quick shout out to the team who helped create this project. Some of them are here today. It's mostly technical artists, but we got help from all over the company, from the URP team to artists and QAs and everything. Okay, thank you.